Section 5.2 is going to go over area problems. Let me give you kind of a nice little overview of where this section is headed by looking at a quick little demo here from Desmos. Our overall goal and a little step towards the fundamental theorem of calculus will be to find the area underneath a curve. Now you can't necessarily do this for just any old curve and get an exact answer until you go through calculus. So right now, without knowing all the fundamentals of calculus, the best thing we can do to try and find the area underneath this curve, say between 0 and 6, is sketch in a bunch of rectangles. Add up the area of the rectangles and then hope that we're close. Eventually what we're going to do is add in more rectangles. So we'll increase the number of rectangles. And as we increase the number of rectangles, hopefully what happens? You're getting a better approximation. So there's a few things that we need to discuss. First of all, we need some new notations called summation notation. It's going to help us neatly and concisely express the area here. We're also going to need to know some formulas that allow us to calculate certain sums. So with that as kind of like an intro of where we're going, let me first talk about the summation notation that I alluded to. And we'll start with problem number 2. You've got this capital letter S in Greek. That's sigma. In fact, when I was brewing more actively at home, I used to name my beers. And the first beer that I named was Sigma Pale Ale. Kind of like that. So, anyways. So this is going to be the sum from 3 to 9. You know, let's make that a smaller number. Well, yeah, we got it as a 9. 3 to 9 of k squared plus 1. So this is what's called your lower limit. And this is your upper limit. Yeah. And for each integer value of k between the lower and upper limit, you're going to substitute in those numbers into this expression. It's called your summons, and then evaluate it. So let's see what that's going to look like. At k equals 3, we've got 3 squared plus 1. And then at k equals 4, you've got 4 squared plus 1, and so on. And we're going to do that for all 7 of these numbers between 3 and 9. So 5 squared plus 1, 6 squared plus 1. So note to self, change that to like a 7 or 6 for the afternoon class. So 7 squared plus 1. Yeah, I know, it's getting a little tedious. But I think you get the idea here. And the idea is just to get you acquainted with this summation notation. So obviously it's a lot simpler to write this sum than to write all this stuff here. So finally the last one, k equals 9 plus 9 squared plus 1. And the good thing here is that we do have, I did work this out ahead of time, you get 287 for the total. So 287. Now the point of this is not necessarily to come up with the numbers, moreover it's to understand this kind of notation. Speaking of notation, let me introduce to you or remind you of another notation that we've dealt with before. At least I think we've dealt with before. So we dealt with something like that before. Yeah, factorials. Okay, so n factorial, 4 factorial is 4 times 3 times 2 times 1. N factorial is n times n minus 1 times n minus 2. All the way down to 3, 2, and 1. So that's your n factorial. Let's do another example using summation notation. Just a quick reminder here, in case you've forgotten, or in case you wanted it on your calculator, 0 factorial is 1, which is kind of cool. So let me give you a summation then. sum from x equals 0 to 3 of x factorial. So what would that be? That would be 0 factorial plus 1 factorial plus 2 factorial plus 3 factorial. So 1 plus 1 plus 2 plus 6 gives me a total of 10. And again, the goal here is to understand this factorial notation and this summation notation. Let's work one kind of the other direction. We're going to start out with a summation and then write it with a sum. 3 factorial is 3 times 2 times 1. So 3 factorial will be 6. All right. I appreciate you checking me on that. Thank you. Let's move up to problem number 8. Problem number 8 looks like this. 9 over 1 plus 1 plus 9 over 1 plus 2 plus 9 over 1 plus 3 dot 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 all the way down to 9 over 1 plus 14. So you've got a sum written like this, but if we wanted to write it more concisely, we can write it with a summation. So it'll be the sum. Now the letter that you choose is up to you. I mean, so far this morning I've used X, I've used K, J is a popular one, I, whatever letter you want to choose is fine. So let's just do J. What should we start out our summation at? 1. Because it's this term that seems to be varying. So J equals 1 up to 14. And now you need a general expression for these terms. So it's going to be 9 over 1 plus what? J. 9 over 1 plus J. So it's a much nicer form to have this in rather than having to write it all out like this. The other advantage of this is that eventually we're going to get to some formulas that you can use that'll help us calculate certain of these summations. Okay, let's try problem number 10. Kind of a little bit of a crazy one, but we'll see what we can do with it. So our expression in number 10 looks like this. 1 minus 1/4 to the second power plus 1 minus 1/4, or give me 2/4 to the second power. And I like this. They go dot, dot, dot. As if they're leaving out a lot, right? 1 minus 4/4 the second power. So really they left off like one term, right? So, all right, but whatever. I pity them. I think it'd be very mind-numbing to have to come up with thousands and thousands of math problems. It would just be overwhelming. So, won't complain here. We want to write this using summation notation. So, it'd be the sum. Let's use an I this time, just to mix things up a little bit. From what to what? All right, 1 to 4. All right. And now you need a general expression for this. So, well, the 1 is consistent in all these. And then we're going to have something squared. What should I put on the inside here? What am I going to square? I over 4. I over 4. So, great. We've written it using summation notation. We're looking okay with that one. All right. Let's try problem number 14. The sum from I equals 1 to 30 of negative 18. So we want to expand this. We want to figure it out. Calculate that sum. Let's start writing out at least a few of these terms. What would it look like? So for instance, when I equals 1, what should I write? Negative 18 plus. When I equals 2, negative 18. And so on, right? All the way down to I equals 30 is negative 18. Now, do I want to sit there with my calculator and add and add and add and add? What's the shortcut here? Good. So negative 18 times 30. Where'd you get 30 from? How many terms? Good. So that's what? Negative 540? What if, and kind of as a nice follow-up to that, what if I gave you the sum from I equals 3 to 7 of negative 18? Now what would you get? Well, here's the rub here. Let's take a careful look at this. So at I equals 3, we got negative 18 plus I equal 4, negative 18 again. So I equal 5. And I'm sorry, this is a little bit repetitive. I equals 6. And then I equals 7. So it's not quite right to say we're going to multiply this by 4. What should we multiply by? 5. So it's going to be negative 18 times 5. So how are you going to amend our little rule here? I mean, it worked out good right up here when we're going from 1 to 30 to take, 30 times that, right? But here it didn't quite work out so well. It even didn't work out well when we did 7 minus 3. How are you going to have to fix things so you can calculate this without adding them all up? How many terms are there going to be in a series like this in general? Plus 1. There you go. So the upper limit minus the lower limit plus 1 will tell you how many terms there are. So the number of terms in the series equals the upper limit minus the lower limit plus 1. And that's something to kind of keep in the back of your mind when you're working with these things so that you don't accidentally multiply by the wrong number here. Yeah, this one's dying. Okay, let me take brief time out here for kind of a little historical problem. One of the most famous mathematicians of all time was a guy by the name of Carl Friedrich Gauss. Gauss is ranked with Newton and Archimedes. In fact, you'll see Gauss's name in like physics. Gauss, I think, is a measure of magnetic force, I think. Yeah. But when he was 10 years old, Gauss was German. He was in a classroom, and his teacher got really, really mad at the class and said, "Okay, here you go. Do this." And he gave this problem to the whole class. Now, let's figure it out using our modern notation. What was he asking him to do? If you expanded this sum, essentially what are you being asked to find? Yeah, add up the first 100 numbers, right? All the way to 99 plus 100. Yay. So, okay, that's what he needed to find. Little 10-year-old Gauss sat there, and back then they didn't have paper and pencil, they had a chalk slate. And he wrote down one number on his chalk slate, cheekily threw it up on the teacher's desk and said, "There it is." And he was the only person in the class that got the right answer. Yeah. Yes.
Just to shut them up.
Exactly. So the teacher wanted to kind of shut him up for a while, and within like 5 minutes, Gauss is like, "There it is." So Can anyone tell me, even using a calculator, what that answer is? 50-50. Good job. So 5,050. But how did he do it? How did he do it so fast? Well, there's a couple possibilities. If we call this S, that's our sum, and then write the sum in a different order, 101, or excuse me, 100 plus 99 plus 98 plus all the way down to 1. So I'm really writing the same thing backwards. Then when I add these things, I'll get S plus S is 2S. And here I get 101. Here I get 101 and 101. In fact, kind of consistent here. I keep on getting 101. So how many of these 101s do I have? 100. So 100 times 101, but that's twice my sum. If I wanted just S, I could divide that sum by 2. And that's my sum, or 50 times 101 is 50-50. So, okay, not so bad, and maybe it took some of the magic out of it. But remember, this is a 10-year-old kid who did it on the fly. Yeah, no calculator, no pen and paper, just wrote down one number. Pretty impressive. It's no wonder why Gauss is at the top of mathematical achievement. Now, we can do a little bit better than this. And that is, we can generalize this for any value of n. And there's actually several formulas. I think I've got them listed on your sheet, the handout there. But let me write them down here, nonetheless. So the sum from I equals 1 to n of I. So basically the sum of the first n numbers is going to be n times n plus 1 over 2. So if you apply that to Gauss's problem, the sum from I equals 1 to 100 of I would be 100 times 100 plus 1 divided by 2. And that's your 50-50. There's two more formulas that I would ask that you know. One of them you kind of almost can get for free, but the second of these is going to be a little bit more of a pain in the butt. What if you added up the first n squared numbers? The formula for that's a little bit more involved. It's n times n plus 1 times 2n plus 1 over 6. Okay. Now, the last one is the sum of the first n cubed numbers. And this one I said you kind of almost get it for free because the formula here is really just the square of this formula. So if I square all these terms, I'm going to get n squared, n plus 1 squared over 4. So it's just the square of that other one. Let's apply these and do some problems. Along the way, I'll show you some other properties of the summation. Remember that these are additions, so they're going to have properties that mirror those things that we know from addition. We'll start with problem number 16. The sum from I equals 1 to 15 of 5i minus 4, like that. Now there's a lot of ways you can do this. You can do this brute force. You can keep on putting in the values I equal 1 to 15, evaluate all these things, and then add them all up. That's not the goal here. The goal is to understand the formulas and use the formulas that we've developed in order to calculate this. So what do I mean by that? Well, I guess I would start by breaking this up. Sum from I equals 1 to 15 of 5i minus the sum from I equals 1 to 15 of 4. Okay, so it's a summation, but it's a summation of that difference. So we'll just distribute the summation over that difference. Now the 5 is a constant. It doesn't depend on I. So I'm going to factor that out. So that's going to look like 5 times the summation from I equals 1 to 15 of I. Minus, now here, this is just a constant, right? So it's 15 times 4. Now if you're being careful, say, all right, well that's 15 minus 1 is 14, but plus 1 back is 15. So we're okay. As long as this summation starts at 1, it's just going to be the upper limit times this. So 15 times 4 is 60. Let's work on this one. The nice thing about where we're at here is that this is something for which we have a known sum. The way we can calculate that is to multiply 15 times 15 plus 1. Let me just write that as 16. And that's going to be what? 120 times 5 is 600. Minus 60 would be 540. Somebody check me on that. I was never really good at math. All right. So 540. Yay. So a lot nicer, I hope, than expanding it all out, writing it term by term, and then adding it up. Boy, that'd be tedious. Although you guys are nothing but tenacious. I've put problems on the test like this before, and people will add them up by hand. So I started upping the ante. I said, all right, well, we'll do a sum from 1 to 100. Nah, that wasn't enough. So finally I did from 1 to 1,000. And I kid you not, one time I had an entire back sheet of a paper covered with the numbers of these sums from 1 to 1,000 and somebody trying to add them up by hand. I actually gave them a point of partial credit because I thought that it was a heroic effort. I appreciated what they tried, but just be aware that on a test I will make these numbers rather large enough, and that has to be at least 2,000 nowadays, I guess, in order to force you to use the formulas. But please just use the formulas. I'll try and keep the numbers nice and round. That way it won't be so bad. How are we looking at 16? We're okay there? All right, so let's try another one like that, problem number 18. In fact, if you want, I can let you try this one. Problem number 18 is the sum from I equals 1 to 10 of I squared minus 1. And again, try and use the formulas. I mean, you can actually do this in other ways, including your calculator to double check it, but as usual, I'm going to want to see the work. You should be filling in these formulas. This is a known formula. It's the sum of the first I squared integers, or n squared, 10 squared integers. So we have a formula for that. It should look like n, which is 10, times 10 plus 1, it's going to be 11, times 2n, which is 20 plus 1, 21, all over 6. How about this total right here? What's that going to be? All right, so that's just going to be 10 times 1, or just 10. So let's see, do some cancellation here. Cancel. So 385 minus 10 would be 375. Cool. Do you want one more of these? All right, let's do problem number 20 then. So the sum, and here's at least a little bit more of a meaningful number, from 1 to 25 of I cubed minus 2I. As with all of these, I would suggest you start by rewriting it, break it up a little bit. That's going to be the sum from I equals 1 to 25 of I cubed minus, I'm going to factor out the 2 outside the summation, 2 times the sum from I equals 1 to 25 of I. And as before, we have formulas for both of these things. We have a formula for the sum of the first I cubed numbers and the formula for the sum of the first I numbers. So let's put in both of those. So we have a formula here and another one here. Let's use both of those. Okay, so filling these things in should look like this. Sum of the first n cubes, we're going to use this formula up here. So we're going to have 25 squared, 25 plus 1 is 26. 25 squared times 26 squared divided by 4. Someone get a number for that one? 104,975. Oh. 625? All right. 105? Okay, thank you. So 105, 625. Minus, let's see, the 2's cancel. 25 times 26 is 650. All right, so 104, 975. 975. Yay. All right, cool. Hopefully you're getting comfortable with the summation notation here. Any more thoughts on 20? We're going to have a chance to practice with our summation notation yet some more. So we're not done with it. So the first part of it was getting used to it a little bit and introducing some of these formulas. The next part is going to be applying this to the calculation of area, and in particular area underneath a curve. So does everyone have this handout? Okay, so let's switch gears and start working on calculating area underneath a curve. So the curve that I have here for us is y equals x squared plus 1. And we're going to look at this curve and calculate the area underneath the curve above the x-axis between 1 and 3. Now when I say calculate, I should probably say approximate. This is the best we're going to be able to do. So how are you going to approximate? Well, we're going to draw a rectangle that is going to estimate the area in this interval of the area underneath the curve. So I'm going to start with the left-hand endpoint of each of these intervals. So this is 1.5, this is 2.5. Start with the left-hand endpoint and draw little lines to the right. And these are going to be my rectangles. I'm going to calculate the height of these rectangles times their width. That'll give me the approximate area. So it's going to look like this. Yay. Now, let's find these areas. So the overall area here is going to be approximated by the sum of these areas. Let's find these area of each of these. So area of A sub 1. Well, okay. I guess we need to remind ourselves that this is y equals x squared plus 1. And I want to try and find the area of this rectangle. There's two things I'm going to need to know. I'm going to need to know the width of this rectangle, which I know, and I'm going to need to know the height. How am I going to find the height? Yeah, thank you. Plug it into the equation. So 1 squared plus 1 is 2. So we have a height of 2 times a width of 1. So, oh yeah, it's a width of 1/2, thank you. So 1 squared plus 1, that's your height, times the width, which is 1/2. So we get the area here is 1. Moving on down to the next rectangle. This time, what's the left-hand endpoint of my interval? 1.5. So I'll put 1.5 into this expression. 1.5 squared plus 1 times 1/2. So it's going to be 2.25. 3.25 times 1/2. 1.625. Okay. And so on. Let's do 2 more to finish out our approximation. The next one's going to be 2 squared plus 1 times 1/2. So that's going to be 2.5, right? 2.5. The last one is going to be 2.5 squared, which is what? 6.25 plus 1, 7.25 times 1/2, 3.625. If I add all these up, I get 8.75. Huh. Do you think that's a good estimate of the area underneath the curve above the x-axis between 1 and 3? Think it's a good estimate? No. Yeah. It's probably a little short, right? All right. So what if we switch things up? What if instead of using the left-hand endpoint, we use the right-hand endpoint? We could do that. So that would look a little different. So here, this time, we're going to estimate the height of our rectangles using the right-hand endpoint. By the way, if you want, I've got rulers up front here. Feel free to borrow one. So here, here. So now it's a different area calculation. We're going to get a different estimate of the total area. Do you think our estimate doing the right-hand endpoint is going to be an underestimate of the true area, or what? It's going to be an overestimate. Still working with the same intervals here. The area of the first one a sub 1 is going to be 1.5 squared plus 1 times 1/2. And this is the same curve as before. Y equals x squared plus 1. We know that from the first part of this, that's going to be 1.625. What expression should I put in for a sub 2? Yeah. 2 squared plus 1 times 1/2. 2.5. So the good news is that at least for the first three of these things, we don't really have to do much new work. But what about the last one? 3 squared plus 1 times 1/2 would be 5. And if you add these up, we get 12.75. And that's an overestimate. Now, a few of you suggested that, well, maybe you should just use the midpoint here. The midpoint would actually do pretty good. And that'd be using the midpoint here in these intervals. Now, it's not a calculation I'm going to go through, but you could. The nice thing about using the midpoint is that although you would get an overestimate here, you get an underestimate here, they tend to cancel each other out. Using the midpoint is actually equivalent to what you would get if you averaged these two together. So if I take 8.75 plus 12.75, add them together and divide by 2, it gives me 10.75. The true answer is 10 2/3. So not too bad. Not too bad at all if you average these things. By the way, when we get around to talking about numerical methods, etc., this is equivalent to the trapezoid method right here. Now, in and of themselves, neither one of these is really a good method. At least when you have this course of what's called a partition. Your partition is the set of points that you use to break up the space from 1 to 3 into subintervals. So let's improve on that. And the way we're going to improve on that is we're going to increase the number of intervals. So let's go back to this idea of, first of all, a partition. So here's some curve. And we want to estimate the area underneath this curve. One way to do this is to start by breaking this curve up into a bunch of different points. Now the endpoints, A is going to be x sub 0. And then this next little cut point is x sub 1. And then x sub 2. X sub 3 in this is the same thing as B. And you can have more and more and more points. And that's eventually what we're going to do, is we're going to keep on adding more and more intervals. And we saw that early on here when we looked at this example. So let me go kind of back here to the beginning. We've got 4 intervals. We're using a left-hand endpoint to get the height of these things. But as you add more intervals, you're going to get a better and better estimate of the true area underneath this curve. Now the cool thing about this is you can actually see what that estimate is. I've got a running total for you right here. So let's watch what happens to that estimate as you add more and more rectangles. So 17 something, 17.85, 875, etc. So as you add more rectangles, hopefully we're getting a better and better estimate of the true area. Now what's this process like of adding more and more rectangles? What's a calculus way of describing it? Yes, n is going towards infinity. So let's just jump to the happy ending here, at least as far as this demo is concerned. 17.9928. All right. What would you guess the actual true area is if you had to do it? Yeah, 18 seems pretty good. In fact, we can kind of cheat a little bit this way. Let's just make that 200. And then fast forward the happy ending again. 17.99995. All right, so I'm pretty sure that the true area is, yeah, 18. All right, but how do you show that without all this fancy stuff? How do you show it with methods more akin to calculus? Let's talk about that next, right here. So one of the things we're going to need calculating this area is an expression for the area of each of these rectangles. There's going to be two parts to that expression: the width and the height. So the expression for that is right here. That's your height times the width. And together, the height of the width, height times the width, gives you the area of one of those rectangles. What's the summation going to do? Summation is going to add up the area of all those rectangles. So we'll probably think of it this way. But the initial definition that you could work with if you're developing calculus from scratch would be the length of these is going to go to 0. The length of the partition. What does that mean? Well, yeah, your partition is the set of all these points. The length of it is considered to be the length of the largest of these subintervals. So the distance between x sub 0 and x sub 1, that's a subinterval. The distance between x sub 2 and x sub 1, that's a subinterval, and so on. So if the length of those gets really, really small, that's great. That's what we want. The length of the largest of those goes to 0 is really, for us, the same as the number of these rectangles goes to infinity. A little bit more on the notational side of things. Delta x, if you have what's called a regular partition, and all these things are evenly spaced, then the width of that partition is going to be the length of the interval divided by the number of subintervals. So in this case, take the length, b minus a, and divide it by 1, 2, 3. That's the width of your subintervals. Okay. I'm going to break this up into two parts. We'll do a part 1 and part 2 for this lecture, just to give you a little bit of a break here for a second. So I'll kill this now, and we're going to come back and do some area underneath the curve problems.